Hi, everyone. It's very nice to be back. Welcome to our talk, Serving the Future, KServe's next chapter hosting LLMs and GenAI models. My name is Alexa Griffith. I am a senior software engineer at Bloomberg, and I'm working on building our AI inference platform.
And my name is Tessa Pham. I'm also a senior software engineer on the AI inference team at Bloomberg. Today, let's come join me and Alexa in the KubeCon AI land to explore what new features KServe has to offer in the age of GenAI. AI is evolving really quickly, and GenAI is transforming industries, from automating tasks, creating content, to making smarter decisions. And as demand skyrockets, companies are also rushing to adopt AI into their products, which drive the need for even more powerful models. But with that growth comes big challenges. We're facing higher compute costs, scalability struggles, and the constant push to balance performance and efficiency. That is where KServe comes in. KServe simplifies AI deployment by handling inference, auto-scaling, and resource management to make it easier for businesses to scale and get the most out of generative models. Deploying GenAI at scale comes with a whole new level of complexity. These models are getting bigger and more intricate, which means they need significant compute power and smart scaling to keep up. So the usual challenges like scalability, reliability, and latency become even tougher to deal with when we're working with these models with this size. And on top of that, figuring out how to use resources efficiently without sacrificing performance is still a major hurdle. To put it simply, making GenAI run smoothly at scale takes more than just raw compute power. It takes the right strategy. So, how does KServe come in to solve these challenges? First of all, KServe sets out to simplify AI model deployment on Kubernetes by abstracting away from the complexity of Kubernetes, allowing developers to focus on building models without having to worry about managing the infrastructure under the hood. KServe supports multiple GenAI and machine learning frameworks, making it versatile and framework agnostic. And in the past year, we've also added support for OpenAI protocol, so now it is compatible with the OpenAI API as well. KServe comes with native features to monitor performance, automatically adjust scaling based on demand, and optimize inference efficiency. And finally, it is now equipped with GenAI-ready features, including LLM metric-based auto-scaling, model caching, multi-node inference, which will help reduce latency and improve response times, and a couple more features. So with all of these powerful tools, KServe can prove to be an ideal solution for the next generation of AI applications. If you're new to KServe, let's take a quick look and see what it is and how it works. Now, if you've been working with KServe for a while, this is probably a diagram that you've seen very often. On a high level, KServe runs on Kubernetes, which acts as an abstract level on top of the hardware level, which is GPUs and CPUs that users would need to have. It's also built with Knative and Istio, which are two other open source projects, to give it serverless capabilities and a service mesh layer. And as you'll see later in this talk, what's great about KServe is how easily it is to integrate with other open source tools to make it a powerful and adaptable solution. KServe serves as a standard model inference platform and provides a Kubernetes custom resource definition called the inference service for serving predictive and generative machine learning models. And thanks to its serverless design, KServe works across multiple ML frameworks to provide a streamlined, high-performance inference protocol. And this whole architecture works together to support pre- and post-processing, inference, monitoring, explainability, and even advanced deployments like canary rollouts, pipelines, and model ensembles with inference graph. So for a long time, KServe has been the go-to open source solution for predictive model serving, with features dedicated specifically to predictive inference needs, such as auto-scaling based on requests, including scale to 0 on CPU and GPU. There's request batching, request and response logging, security with Auth.z. You have basic traffic management, and also out-of-the-box observability with metrics and distributed tracing. However, running generative models is way more demanding than traditional predictive inference, mainly because of the massive size of the models and their complexity. Large language models, for example, need high-powered GPUs, TPUs, or even specialized AI accelerators, which makes it critical to efficiently allocate compute resources in order to balance out cost and performance. On top of that, these models must scale dynamically, which means that they must be able to handle traffic spikes without over-provisioning and adjust resources as demand fluctuates. Another big challenge is latency, especially for real-time applications like chatbots where we need almost instant responses. And that is why we need to optimize model loading, caching, and request routing. And with some models now reaching terabytes in scale, storing and loading them efficiently is also a priority. And finally, engineering teams often need to manage multiple LLMs at once, which means unified model management is also key to keep everything running smoothly on your platform. So if you already have your platform running on KServe or looking to integrate KServe into your stack, here are some new features you will get from KServe to support your GenAI model deployment. First of all, we have built-in metric-based autoscaling. So instead of just autoscaling based on requests, each POS capacity can now be determined using an LLM metric like token throughput or time to first token. We have implemented model caching, which utilizes local persistent volumes to reduce download time of storage initializer. And if you're using KServe with VLM, you can also get multi-node inference and prompt caching out of the box. We've also added OpenAI protocol compatibility, as mentioned before, which supports chat completion and embedding tasks. KServe's observability is also enhanced with LLM metrics like, again, time to first token, token throughput, etc. And now the tool can be integrated with Envoy AI Gateway to manage traffic more efficiently in hybrid use cases where external models are used alongside with self-hosted models. So with these added features, KServe now supports both traditional and generative inference. This is the full architecture of KServe for the age of GenAI. On the control plane, you see that we've added a model cache controller and the Kata external scaler. And on the data plane, there's optional integration with Envoy AI Gateway to enhance traffic routing, as mentioned before. We've also introduced OpenAI compatibility, LLM rate limiting, and intelligent model routing to optimize performance. Now we'll dive into some of the key features and see how they all come together and fit into this whole architecture. The first feature we want to talk about is model caching. Model sizes are growing exponentially. They used to just be a few gigabytes, but now they're reaching to hundreds of gigabytes or even terabytes. That means downloading and starting a model takes a lot of time. And when you're scaling up, every second counts. So the faster model can load, the quicker your inference service can scale and recover when needed. That's why KServe has introduced a solution to cache models locally, which will cut down startup times and make scaling and auto-scaling much more efficient. With KServe local model cache, you simply can specify where your model is stored and which node groups you should cache it. This cache works as a Kubernetes custom resource. So this whole local model cache is a CRD. So when you create the custom resource, KServe will be able to handle the rest. The model cache controller, as you've seen in the diagram before, it will launch download jobs to pull the model from the model registry onto each node. and then it will set up persistent volumes and attach them to inference pods using PVCs. And a cherry on top is that the model cache mechanism is self-healing. So you see in this diagram, on each node, you have a model node agent. And this agent is present on every node, and it continuously cycles through all the model caches. And when it detects a missing model, it will automatically try to re-download it from the model registry. So if the cache is wiped out for whatever reason, this agent will be able to recover it for you. This entire integration is seamless because KServe can now detect local PVs automatically, so there is really no extra work for users except to create just a couple CRs. So this is what a YAML for a model cache, a local model cache CR looks like. As you can see, it's pretty concise. You just specify the name of the inference service. The spec is you need to specify the model size and the node groups that this model should be cached on. And finally, the model storage URI, so where it can be downloaded from. Once this CR is created, and then the controller can detect the CR, and it will spin up download jobs and try to download the model onto these nodes, the CR will be updated with a status. And this status indicates that the model has been downloaded into 4 nodes, so there are 4 copies, the name of the inference service, and what is the status of the model cache on each node. Now that we have model cache, let's talk about autoscaling. Autoscaling, we already have autoscaling, request-based autoscaling on KServe. But this is another feature that has been enhanced to better support generative model serving. Now your inference service can scale automatically based on a LLM specific metric like queue size, KV cache size, or token throughput. Or you can also specify a combination of these metrics. Without giving too much away into the implementation details, because there is a deep dive talk later on Thursday to talk about how autoscaling is implemented in KServe. This is just a high level how you can add autoscaling into your service. So here on the right side, you'll see the YAML or the CR for the inference service. And the extra part that you need to specify is the autoscaling part, specifying the metric to trigger the auto-scaling. So for example, in this YAML, we want to pull the metric from OpenTelemetry, and we want to sum up the GPU cache usage percentage and take the average of it over time, and the time here is set to 60 seconds fixed. And you specify the target, so once this number hits that target, the auto-scaling will be triggered. And another thing is KServe's autoscaling is highly responsive because real-time metrics are now being pushed directly to the autoscaler for faster scaling decisions.
Okay, so for predictive inference, we had a unified API in KServe. We still have that, but for generative inference, we added some OpenAI protocol support as well. So right now, we support 3 different endpoints: the completions, chat completions, and embeddings endpoint. We plan to add more support as well later. Let's talk a bit about multi-node inference with VLM. So for an H100 node, for example, with 8 GPUs, let's say we have 80 gigs of memory each, so we have around 650 gigabytes of memory available. This means that the DeepSeek model that we showed in an earlier slide, that's going to reach around 1 terabyte, exceeds this memory capacity for a single node. So somehow we need to support the ability to run multi-node inference, right? So we do this using Ray Cluster with VLM, offering both tensor and pipeline parallelism to serve our multi-node inference feature. So basically, each inference service becomes like a superpod with, which manages a Ray cluster fleet, which can have a head and worker nodes for running this distributed inference. Let's talk about another feature that we add to enhance GenAI workloads, which is prompt caching. So again, a single pod can't hold all of the cache because it's large. So since our GPU memory is limited, we need to externalize this cache. So VLM, which is, as you all may know, a high-performance inference engine that's optimized for running large language models, supports prompt caching out of the box with via KV cache. So basically, KV cache stores key value matrices from previous steps in a transformer model to speed up our inference by reusing computations. However, KV cache has some challenges with growth. And as we can see here, with just 1,000 or 10,000 tokens, we have 16 gigs in the KV cache. And as you can see, as you add more zeros, it grows exponentially as well. So depending on the sequence length, KV cache can grow to be pretty large. So we need to add another solution. So looking forward, this is what we are planning, that we're in progress implementing, is LM Cache with KV Cache. So what is LM Cache? LM Cache is an open source system designed to manage your KV cache efficiently. So this makes KV cache more scalable by caching common input prefixes, helping to reduce these redundant computation and to speed up repeated queries. So like things like document processing, chat history. So what this does is it makes the access and storage of caches faster, especially for these things like long documents and multi-turn conversations. What's great about LM Cache is that you can share and store across multiple VLM instances. You can route queries to the instances that already hold the relative context and the KV cache. This is shown to be able to reduce time to first token by around 3 to 10 times and save on the GPU cycle reduction. So this is a very basic architecture of using our LLM workloads with KServe. As you can see, we have a client application that hits some load balancer. Maybe we have just some generic gateway, let's say Envoy gateway. And in our inference cluster, we're running some self-hosted models, say like Llama, Mistral, like any self-hosted models. So let's talk about how we could improve this basic architecture. Well, the first step we can do is implement the Envoy AI Gateway with KServe. So what does Envoy AI Gateway give us? It gives us this seamless AI integration, so it enables hybrid cloud model serving very easily. We have this resilient routing that assures that we have high availability, smart traffic management to our models. Also, we have token-based rate limiting. So we have token-based autoscaling in KServe, but from the Envoy AI Gateway perspective, we can also implement token-based rate limiting rather than just the normal request weight limiting. So this controls our request flow, giving us, again, optimized performance. Again, we have enhanced observability and metrics on this layer. So standardized logging, monitoring, reporting, like cost reporting with tokens. And now we can more easily treat our LLMs as a service. So we can deploy and scale our LLMs very easily across cloud and prem because we have this centralized and unified API and authentication for LLMs. So no matter what LLM provider you're using, the access pattern is going to look the same. So let's again look at, if we implement the Envoy AI Gateway, what our architecture would look like. So this is an architecture that we run as well. So we have our AI workloads that are, you might have some in a hosted cluster, like that you self-host. Could be a managed cluster on your own. I mean, it could be in AWS or it could be on-prem. And you can also connect easily to any LLM provider, AWS Bedrock, Azure OpenAI. And what's great about the Envoy AI Gateway is you get all these features. And from a client perspective, it's really easy. You just give the model name, and based on the route in the Envoy AI Gateway, it automatically knows where to route it to. So it makes it super easy to have a platform and build a platform with KServe and other environments. So let's discuss another further optimization for a component in our architecture. So if you are running KServe and self-hosted models, you can also implement this Gateway API extension. So what does this do? The Gateway API inference extension gives you better metrics and insights. It tracks cache location, model placement, and pod capacity. And this is a Kubernetes native extension of the just ingress API extension as well. So this is just built for GenAI models, specific for them as well. So we get pod capacity is another insight we get. We get smarter routing. So on this level, it routes requests based on like loads optimized for inference and not just round robin. It can route based on model name, upgrading from traditional path-based routing. And also, it can implement serving priorities. So prioritize models based on how critical they are, giving higher priority to latency-sensitive tasks. Also, it helps, again, on this level, optimize resource use. So it improves things like efficiency, scaling, and latency. Again, we're talking about building KServe and using it as a platform, and especially since LLMs are getting larger and open source models are more common, we're looking to kind of shift to thinking about LLMs as a service. And in the hybrid cloud with Envoy AI Gateway architecture, we show that, but also, as we know, resources can be limited, so we want to be able to provide our users, our AI engineers, with a platform they can easily use that can help to optimize our resources and use them better. One way we can do that is through batch inference. So this is, again, we would implement the, we are implementing the OpenAI protocol with this to have a batch architecture. So this just shows with KServe and Envoy AI Gateway how you can implement another architecture to help optimize performance and help to serve your LLMs as a service. Again, another thing that we are looking forward and in progress of implementing, another further optimization. So latency for GenAI models isn't very predictable because there are these two steps that have two different restrictions. One's compute bound and the other is memory bound. Prefill is compute bound and decoding is also memory bound. So prefill needs GPU compute on the fly, and decoding has a slightly different need. It needs to access the KV cache and use the results from the prefilling stage. So they do depend on each other, but they have different needs. So we can separate these two, execute them independently, and on different GPUs. And this can help to increase our performance, our throughput, optimize our hardware for each stage. So this is another optimization that we're in progress of developing. So that was a lot, and just to wrap it up, some of our key lessons learned and takeaways since we are running this at an enterprise scale. So latency versus throughput. We like to, give our AI engineers the knobs for them to tune to best fit the needs of their models. For example, depending on the model or the use case, there might be a large model that some requests need to hit, but certain requests, it might be better if they hit a smaller model and help us to optimize our performance. So what we're trying to do as a platform team and with KServe is just give them those knobs so that they can tune based on their needs, based on their use case. So considering latency versus throughput, considering the trade-offs, and giving them the things they need to be able to tune it correctly. Additionally, optimizations matter. So again, all of these features are different optimizations: KV caching, prompt caching, model batching, model caching, token-based autoscaling, token-based request limiting. All are things that can help us improve the performance. Again, we're starting to shift to think of our LLMs as a service and how we can host them to have better optimizations and better use of our resources. So AI Gateway and KServe together can enable this seamless on-prem and hybrid experience with model serving. Additionally, observability is key. So for GPU capacity planning and benchmarking, we need to ensure efficiency, and having these different ways to observe our model, which all of these tools and features give us, are really helpful. Another thing as a platform team that we've been thinking about are the SLAs and SLOs for LLMs. There are certain things that you need to consider, like time to first token and all of these different things that we need to consider as a platform team, how to create a very reliable platform, which we're doing a talk on later tomorrow also.
All right, so if you're interested in working with or contributing to the project, you can get started with these resources. And Bloomberg is also hiring, so come talk to us at our booth in the expo halls when the main conference starts, if you're interested in being part of the AI journey at Bloomberg. All right. Thank you for being here for our talk, and we have like 1 minute left for maybe one question.
Thank you very much. Thank you. So we do have time for questions, so go ahead. Yeah. I will just ask the next speakers to come forward if possible so that we speed up after. Yeah, go ahead.
Hi, thanks for the session. My question is, you started showing the general KServe diagram where Knative Plus is still shown, and then you introduced Envoy AI Gateway. How would that fit into that picture? Is like an alternative like model mesh, or?
Oh, you're asking how Knative and Istio fit in?
Yeah.
Yeah, we still use Knative and Istio under the hood. Yeah, you want to answer?
For the LLM serving, we actually moving away from Knative. So because Knative traditionally is request-based auto-scaling. And for the LLMs, we are currently moving to direction for using Kita currently. So that gives us a lot more flexibility how we can scale based on any of the metrics, if that answers the question.
Thank you.
Hi. This is a great talk. It covered a lot of the, I think, requirements for an advanced inferencing server, inferencing platform. I was curious when it comes to NVIDIA Dynamo, is that something that you see embracing that technology since it's open source, or do you see doing something that's complementary or competitive with that?
At Bloomberg, we do try to integrate with, and we implement this, or we have this value in KServe too. We do try to implement with open source projects like VLM. So I'm not 100% sure, but I'm sure that we would try to integrate if we can, as long as everything works out, right?
Hi, great talk. Quick question, do you run single model multi-node deployment workloads? And if so, do you support or planning to support some kind of topology awareness?
Yes. I mean, yeah, for example, the DeepSeek model, it needs to be multi-node.
So topology, we currently don't quite support. So like, are you talking about the hosting model? Like, can you repeat the question again? Sorry.
Yeah, so I'm wondering, like for single model multi-node types of deployments, do you have some kind of mechanism so that the nodes participating in inference, they actually have some kind of network locality, so they are in close proximity to each other?
I think you should be able to do using the Kubernetes like a topology. What is that called? Awareness, like scheduling. If you want to co-locate all the pods on the same node. For especially the workers and head workers, head node and the worker nodes, right?
Cool, thank you.
Yep.
All right, so apologies for the 2 remaining questions, but we do have to move to the next session. So I suggest maybe if you can come and ask the questions directly, but let's thank again for the great talk. Thank you.